Now in this lecture we'll find out the radius of the small circle. In the drawing we have a right triangle ABC. This is the right triangle ABC. We know that side AB equals to 5 units in its length. Side BC equals to 8 units in its length. Inside this right big triangle ABC we have this small circle and we have also this big semicircle, and our mission is to find out the radius of this small circle. So first of all we will implement the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I write it down. Here by PT is the relation for Pythagoras theorem. So AC square must be equal to AB square plus BC square. AC is the missing side, so we leave it as it is. So AC square equals to AB square. Here AB equals to 6 units in its length. Therefore AB square is 6 square, this is 36. Plus BC square. BC equals to 8, therefore BC square is 8 squared, that is 64. So in total we actually found out that AC square equals to 36 plus 64. 36 plus 64 is 100. So we found out actually that AC square, that is the square of the hypotenuse, equals to 100. We take a root out of this equation, we found out that the missing tangent AC is equals to the square root of 100, that is 10. So here, the hypotenuse AC equals to 10 units in its length, so I write it down. AC equals to 10 units in its length. We will define the point of tendency of tangent AC, that is the opposite AC. So we define the point of tendency of tangent AC with this big semicircle. This point is point H. So here we can implement rule 2, because if you focus on this coming sum point A, from this coming sum point A, we have two tangents to this big semicircle. We have tangent AB and tangent AH, and according to rule 2 they are equal to each other. That is to say AB equals to AH. So I write it down. According to rule 2, the length of tangent AB must be equal to the length of tangent AH. So they are both exiting from this coming sum point A. But it is given as the equation that AB equals to 6. So we can write here that AB equals to 6. And from this equation, 6 equals to AB equals to AH, we derive that AH is also equals to 6 units in its length. So this is 97 AH, and it is equals to 6 units in its length. What is the length of the missing 97 HC? The missing 97 HC equals to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. So I write it down. So we found out that the length of this 97 HC is equals to 4 units in its length. In the next step, we define the center of this small circle. This point is point P. We define the center of this big semicircle. This point is point Q. We define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent AC with this small circle. This point is point K. And we define the touching point between this small circle and this big semicircle. This point is point L. In the next step, we will join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is the point of the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B. Therefore, QH equals to B. It is the radius of this big semicircle. Here we can implement rule 1 because we have the radius QH is 1 to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Here, this is angle C. Angle C is a common angle that belongs both to the big right triangle ABC, and this angle C also belongs to the right small triangle HQC. This is the right small triangle HQC. So we define the size of this angle, angle C, as alpha. And we'll focus on this right small triangle HQC. In this right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on the big right triangle ABC. The big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, angle ABC equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. According to the same rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the big right triangle ABC is similar to this small right triangle HQC. So I write it down. The big right triangle ABC is similar to this small right triangle HQC. So why the big right triangle ABC is similar to this small right triangle HQC? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle ABC in the right big triangle ABC. And it is equal to this angle, that is actually angle QHC. This one right triangle QHC. So repeat again, we should found out that angle ABC in the big right triangle ABC equals to angle QHC in the big right triangle QHC. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if you relate to this angle alpha, as it belongs to the big right triangle ABC, it will be defined as angle ACB. And angle alpha equals to itself. So if we relate to angle alpha as it belongs to the small right triangle edge QC, it will be defined as angle edge CQ. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually, this is angle BAC in the big right triangle ABC, and it is equal to this angle. It is actually angle edge QC in the small right triangle edge CQ. Repeat again. Actually found out that angle BAC, the big right triangle ABC, equals to angle edge QC in the small right triangle edge CQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in the big right triangle ABC are correspondingly equal to all the triangles in this small right triangle HQC. Therefore we actually proved that the big right triangle ABC is similar to this small right triangle HCQ. According to angle similarity rule. So I write it down. We actually proved that the big right triangle ABC is similar. This is the sign of similar to the small right triangle HCQ according to angle similarity rule. And from the fact that the big right triangle ABC is similar to this small right triangle HQC, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HQC. Repeat again. We will derive that side AB, the big right triangle ABC, over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle SCQ. AB is 6 over HQ. HQ is B, that is the radius of this big semicircle, equals to BC. BC is 8 over HC. We already found out that HC equals to 4. So in conclusion, we actually found out that 6 over B equals to 8 over 4, that is 2. So 6 over B equals to 2. We'll multiply this equation by B and finally get that 6 equals to 2 times B. We divide this equation by 2 and finally we get that the radius B of the big semicircle equals to 6 over 2, that is 3. So the radius B of this big semicircle equals to 3 units in its length. This is point Q, that is the center of this big semicircle. This is point B, that is the point on the big semicircle itself. Therefore QB is also the radius of this big semicircle, that is equals to 3 units in its length. QB equals to 3. This is the radius of the big semicircle. So I write it down, QB equals to 3 units in its length. In the next step, we join points P and N together by a straight line. Pn is of course the radius of this small circle. We define the radius of this small circle as A, therefore Pn equals to A. A is the radius that we are looking for in this question. So here we can implement rule 1, because according to rule 1 we have the radius Pn that is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. PK is of course the radius of this small circle that equals to A according to our definition. Again, we have the radius PK that is drawn to point K, that is the point of tendency of tangent AC with this small circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we'll implement rule 15 in this drawing. I will present to you rule 15 and we will implement rule 15 in this drawing. According to rule 15, if from an external point of a circle, you will draw two tangents to that circle. So here we have the external point, point P. From this common external point, P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing those two tangents PA and PB, we created here angle APB. This is angle APB that was created by drawing the two tangents PA and PB to this circle. Then the angle that will be created between the two tangents, that is to say angle APB, is created by drawing the two tangents PA and PB. So this angle APB, its angle bisector must pass through the center of the circle. So the angle bisector of this angle PAB must pass through point O, that is the center of this circle. So whenever you draw two tangents from a common external point P towards a circle, you will create angle PAB. So the angle bisector of this angle PAB must pass through point O, that is the center of this circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this common external point A, from this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing the two tangent AK and AN towards this small circle, we created here this angle A. Again, by drawing the two tangents AK and AN towards this small circle, we created the angle A. This is angle A, and according to rule 15, the angle bisector of this angle A must pass through point B, that is the center of this small circle. Again, the angle bisector of this angle A that is created by drawing the two tangents AK and AN towards this small circle, the angle bisector of this angle A must pass through point B, that is the center of this small circle. So, I will draw the angle bisector from point A, of course, and the angle bisector of angle A must pass through point A, according to rule 15. The angle bisector of angle A, of course, must pass through point A, and according to rule 15, the angle bisector of this angle A also must pass through point B, that is the center of this small circle. So actually, according to rule 15, AP is the angle bisector of this angle A. So if the size of angle A in total equals to 2 theta, the angle bisector AP bisects angle A into 2 halves. Each half must be equal to theta. This is angle theta, and this is also angle theta. Again, the angle bisector AP passes through point P, that is the center of this small circle, according to rule 15. It must pass through point P according to rule 15, that is the center of this small circle. Likewise, we will continue to focus on this common example point A. From this common example point A, we have to, so I'll write it down actually. We actually found out that the angle bisector of this angle A, that is AP, must pass through point P, that is the center of this small circle. So right now, I actually found out that the angle bisector of angle A passes through point P, that is the center of this small circle. Likewise, we continue to focus on this common example point A. From this common example point A, we have tangent AB and tangent AH to this big semicircle. Actually, by drawing tangent AB and tangent AH, we actually created the same angle A. Again, by drawing point AB and by drawing tangent AB and tangent AH towards this big semicircle, we created here the same angle A. And according to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A, according to rule 15, must pass through point Q, that is the center of this big semicircle. So I will draw the angle bisector of angle A, and it of course passes through point A, and the angle bisector of angle A must pass also through point Q, that is the center of this big semicircle, according to rule 15. So, in conclusion, you can write down that angle bisector, the same angle A, must pass also through point Q, that is the center of this big semicircle. So I write it down. The angle bisector of angle A passes also through point Q, that is the center of this big semicircle. And it is obvious that the angle bisector of this angle A must also pass through point A. So I write it down, the angle bisector of this angle A must also pass through point A. Is obvious? So the angle bisector of the same angle A, passes also through point A. In conclusion, we should find out that the angle bisector of this angle A passes through point A, P, and Q. So write it down. In conclusion, we should find out that the angle bisector of this angle A passes through point A, P, and Q. Write it down. The angle bisector of angle A passes through points A, P, and Q. Repeat again, the angle bisector of this angle A passes from point A to points A, P, and Q. And the angle bisector of any angle is a straight line. Again, the angle bisector of any angle is a straight line. So the angle bisector of angle A is a straight line. That is to say, all the 3 points A, P, and Q are located on the same straight line. That is the angle bisector of A, P, and Q. Because angle bisector of angle A is a straight line. So all the 3 points A, P, and Q are located on the same straight line. So I did know. I should find out that all the 3 points A, P, and Q are located on the same straight line. Again, they are located on the straight line that is the angle bisector of angle A. Or we can write down that points A, P, and Q are one straight line. Okay, points A, P, and Q are one straight line. Because they are located on the same straight line, therefore they are one straight line. Or line segment A, P, Q is one straight line. So let it know. Line segment APQ is one straight line. But again, if we found out that line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also one straight line. AQ is one straight line. So if AQ is a straight line, it means that shape ABQ is a right angle. Shape ABQ is a right angle. So write it down. In conclusion, we found out that this shape ABQ is a right angle. Okay, shape ABQ is a right angle. Because again, because of the fact that AQ is a straight line, therefore shape ABQ is a right angle. And in the right angle ABQ, this is angle theta, but this angle theta is a common angle that belongs also to this right small triangle ANP. In conclusion, we should found out that angle theta is a common angle that belongs both to the right small triangle ANP, and angle theta also belongs to the right big triangle ABQ. Okay? And again, we should found out that this angle theta is a common angle that belongs both to the right big triangle ABQ, and angle theta also belongs to the right small triangle ANP. This right small triangle ANP. The next step will focus on this right big triangle ABQ. In the right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this perpendicular angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we'll focus on this right small triangle ANP. In the right small triangle ANP, this angle equals to 90 degrees, this angle equals to theta, of course, this angle equals to 90 degrees. Therefore, this perpendicular angle must be equal to 90 degrees minus theta, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the right big triangle ABQ is similar to this right small triangle ANP. So write it down. We prove that this right big triangle ABQ is similar to this right small triangle ANP. So write the right small triangle ABQ is similar to this right small triangle ANP. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So really this is angle ABQ in the right big triangle ABQ. And it is is equal to this angle, that is actually angle A and P, in the right small triangle A and P. Repeat again, angle ABQ in the right big triangle ABQ equals to angle A and P in the right small triangle A and P. They are both equal to 90 degrees, therefore they are equal to each other. In addition, as I already mentioned before, this is angle theta. That is a common angle, it belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to this angle theta as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it equals to itself. So if we relate to this angle theta as it belongs to the right small triangle A and P, it will be defined as angle NAP. Again, this equation means that angle theta equals to itself. We just called to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually, this is angle AQB in the right big triangle ABQ, and it is equal to this angle that is actually angle APN in the small right triangle ANP. Repeat again. We actually found out that angle AQB in the right big triangle ABQ equals to angle APN in the right small triangle A and P. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the triangles in this right big triangle ABQ are correspondingly equal to all the triangles in this small right triangle A and P. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the right big triangle ABQ is similar, this is the sign of similar, to the right small triangle ANP according to angle similarity rule. And from the fact that the right big triangle ABQ is similar to this right small triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB in the right big triangle ABQ over side AN in the small right triangle ANP equals to side BQ with the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we leave it as it is. And it is equals to BQ. BQ is the radius of this big semicircle. This is equal to 3 units in its length over NP. NP equals to A. That is the radius of this small circle, that is the radius that we're looking for in this question. So in conclusion, we actually found out that 6 over an equals to 3 over a. Here we cross multiply this equation, and we get that 6a equals to 3an. Here we'll divide this equation by 3, and finally we get that the missing side an equals to 6a over 3. 6a over 3 is 2a. In conclusion, we actually found out that this missing side an equals to 2a units in its length. So an equals to 2a, ab equals to 6, according to what is given as the question. ab minus an equals to nb. Again, nb equals to ab minus an. ab 6, an is 2a, therefore in total nb equals to 6 minus 2a. So write it down, nb equals to 6 minus 2a. In the next step, we will do a construction. That is to say, from the center of this small circle, that is to say, from this point P, we will draw a perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can do quadrilateral NP BQ. Inside quadrilateral NP BQ, this is point B. Inside quadrilateral NPBQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBQ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to this quadrilateral NPBQ as a rectangle because it has 4 right angles. So write it down, this quadrilateral NPBQ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in a rectangle NPBZ, side NP must be equal to the opposite side BZ. But NP is A, therefore BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ, but NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of the missing line 7 ZQ? From the domain it is very easy to see that ZQ in total equals to BQ minus BZ. Again, BQ minus BZ equals to ZQ. So ZQ in total equals to BQ that is 3 minus BZ that is A. So in total ZQ equals to 3 minus A. So I write it down. I should found out that this is in 97 ZQ equals to 3 minus A units in its length. What is the length of 97 PQ? We'll find out what is the length of line 7 PQ by implementing rule 10 in our drawing. In our drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at this point, point L. Whenever you have an external notch between two circles or semicircles, you can implement rule 10. Now, I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass through their touching point. In the drawing we have two circles. Those two circles have an external notch between them at this point, point P. That is to say, they are touching each other externally at this point, point P. The center of this small circle is here at point M. The center of this big circle is here at point O. With the straight line that connects the centers together is of course the straight line MO. So this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point N. Therefore, we can implement here rule 10. According to rule 10, here the center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. So this straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through their touching point, that is point L. Or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, it means that PQ is also a straight line. So what is the length of PQ? Because of the fact that PLQ is one straight line, it means that PQ will be equal to PL plus LQ. So I write it down. In total, the length of line segment PQ is equals to PL plus LQ, only because of the fact that PLQ is one straight line. PQ equals to PL plus LQ. So PQ equals to PL. PL is the radius of this small circle, that is the radius that we are looking for in this question, and PL, the radius PL equals to A. LQ is the radius of this big semicircle, that is equals to 3. So in total, PQ equals to A plus 3. PQ equals to A plus 3. In the next step, I'll copy this right green triangle PZQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PZQ. Again, the hypotenuse PQ equals to A plus 3. Here by PT is the abbreviation for Pythagoras theorem. Luckily, this is the right green triangle PZQ that I copied from the original drawing. We already found out that PZ equals to 6 minus 2A, ZQ equals to 3 minus A, and the hypotenuse PQ equals to 3 plus A. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So I write it down. PQ square, that is the square of the hypotenuse, must be equal to PZ square plus ZQ square. PQ is A plus 3, therefore, or PQ is 3 plus A, therefore PQ square is 3 plus A square. And it is equal to PZ square. PZ is 6 minus 2A, therefore PZ is 6 minus 2A square plus ZQ square. ZQ is 6 minus A, therefore ZQ is 6 minus A square. In conclusion, we shall find out that 3 plus A square equals to 6 minus 2A square plus 3 minus A square. Here we'll open the brackets on both sides of this equation, and we get that 3 plus A square equals to 3 squared, that is 9, plus A square plus 2 times 3 times A, that is 6A, and it is equal, on the other side of the equation we have 6 minus 2A square. 6 minus 2A square equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A, plus 3 minus A square. 3 minus A square equals to 3 squared, that is 9, plus A square, minus 2 times 3 times A is minus 6A. So here we have 9 on both sides of the equation, so 9 will get cancelled. And we have also A square on both sides of the equation, so A square also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6A. In the other side of the equation we have 36 plus 4A squared. Here it is minus 24A. It is minus 24A. Minus 24A minus 6A is minus 30A. In conclusion, we shall find out that 6A equals to 36 plus 4A squared was 38. Here we'll subtract 6A from this equation, and finally we get, in the side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 36 plus 4A squared minus 38 minus 6A is minus 36A. Here we will divide this equation by 4, and we get that 4A squared over 4 is A squared, minus 36A over 4 is minus 9A, and 36 over 4 is 9. In conclusion, we actually found out that 0 over 4 is 0, of course. In conclusion, we actually found out that A squared minus 9A plus 9 equals to 0. This is a quadratic equation. I repeat again. We actually found out that A squared minus 9A plus 9 equals to 0. So actually this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0. The variable that we are looking for in our specific quadratic equation is a. So x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And finally, the coefficient c equals to 9. Now, the only thing that is left to do is to put the data inside the general equation for x, and we find out the value of the values of a. Why? Because x equals to a. A is the radius of this small circle. That is the radius that we're looking for in this question. So we put the data of our specific quadratic equation in this general formula for x in order to find out the value of the values of a. We do it now, and we get that x equals to a, so a equals to minus b. b is minus 9. b is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. b is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. a is 1, so minus 4 times 1 is minus 4 times c. c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2a. a is 1, so 2a is 2 times 1, that is 2. In conclusion, I should found out that a equals to 9 plus minus square root. Inside the root we have 81 minus 46. 81 minus 46 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. This expression 9 plus square root of 45 over 2 is greater than 3. That is to say, we actually found out that a, that is the radius of this small circle, it is greater than 3 units. But it is actually impossible that the radius of this small circle is greater than 3. Why? Because of the fact that the radius of this big semicircle equals to 3 units. The radius of this small circle must be less than 3 units. So the answer, the solution that the radius a is greater than 3 is the incorrect solution. So we cancel the solution, and we take into account only the second solution that is possible for a. The second solution that is possible for a is a equals to 9 minus square root of 45 over 2. Forty-five is 9 times 5, so we substitute 45 in this equation by 9 times 5, and do it now, we get that a equals to 9 minus 45. 45 is 9 times 5 over 2. So a equals to 9 minus the square root of 9 is 3. Inside the root we left only with 5 divided by 2. In conclusion, we found out that the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units in its length, or in terms of numbers, is equals to 1.146 units in its length. Repeat again, we actually found out in conclusion that the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, so in terms of numbers, the radius of this small circle a equals to 1.146 units in its length. This is, of course, less than 3 units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have the big triangle ABC. We know that side AB of triangle ABC equals to 6 units in its length. Side BC of this triangle ABC equals to 8 units in its length. This is angle ABC, that is the right angle. Inside this big triangle ABC, we have this small circle, and we have also this big semicircle. The small circle touches this big semicircle at this point, point L. And our mission is to find out the radius of this small circle. So first of all, we implemented the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this right triangle ABC is AC. Therefore, the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again. The right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus BC square. The hypotenuse AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36. Plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, AC square equals to 36 plus 64, that is 100. AC square equals to 100. We took a root out of this equation and finally found out that the length of the hypotenuse AC of the right triangle ABC equals to the square root of 100, that is 10. So here AC equals to 10 units in its length. Okay. In the next step, we defined the point of tendency of tangent AC with this big semicircle. This point is point H. Here we can implement rule 2. Why? Because if we focus on this common extent point A, from this common extent point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. And again, according to rule 2, AB equals to AH. Rule 2 states that the length of two tangents from a common extent point to a circle are equal. According to rule 2, AB equals to AH, but it is given as the equation that AB equals to 6. So AB equals to 6, and from this equation 6 equals to AB equals to AH, we will derive that AH equals to 6. So this is AH, that equals to 6 units in its length. What is the length of the missing line segment HC? From the drawing, it is very easy to see that HC equals to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. Okay. In the next step, we join points Q and H together by a straight line. Point Q is the center of this semicircle, point H is the point on the semicircle itself, therefore QH is the radius of this semicircle, big semicircle. We define the radius of this big semicircle QH as B. Here we can implement rule 1 because we have the radius QH that equals to B. The radius QH is 1 to point H, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Here, this is angle C. this is angle C, that is a common angle. Angle C belongs to the big right angle ABC, and this angle C also belongs to the right angle HQC. So angle C is a common angle, that belongs to both triangles. So we defined the size of this angle C is alpha. In the right angle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that this big right triangle ABC is similar to this small right triangle HQC. So why the big right triangle ABC is similar to this small right triangle HQC? First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles in this big right triangle ABC are correspondingly equal to all the triangles in the right small triangle HQC. Therefore, we actually proved that those two right triangles are similar to each other according to angle similarity rule. So I repeat again, we actually proved that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle HCQ according to angle similarity rule. And from the fact that the right big triangle ABC is similar to the right small triangle HCQ, we will derive that the following relationship exists between their sides. We will derive the side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HQC. Repeat again. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB 6, HQ is the radius of this semicircle that is B, according to our definition, and it is equals to BC. BC is 8, and HC is 4. In conclusion, if we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So in conclusion, if we found out that 6 over B equals to 2. We multiply this equation by B and finally found out that 6 equals to 2B. Here we divided this equation by 2 and finally found out that the missing radius B of the big semicircle equals to 6 over 2, that is 3. So this is the radius HQ is equals to B equals to 3 units in its length. QB is also the radius of this big semicircle, therefore it is equals to 3 units in its length. In the next step, we join points P and N together by straight line. Point P is the center of this small circle, point N is the point on the small circle itself, therefore Pn is the radius of this small circle. That is the radius that we are looking for in this question. We define the radius Pn is A, the radius of this small circle is A, so therefore Pn equals to A. Here we can implement rule 1 because we have the radius Pn that is equals to A, the radius Pn is known to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is known to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and N to P and K together by straight line. PK is of course the radius of this small circle that is equal to A according to our definition. Again, we have the radius PK that is on to point K, that is the point of tendency of tangent AC with this small circle. And whenever your radius is on to the point of tendency, then tangent AC will be perpendicular to the radius PK. If AC is perpendicular to PK, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, I presented to you rule 15 and we implemented rule 15 in our drawing. So a bit quickly on rule 15. According to rule 15, if from an external point of a circle, you draw two tangents to that circle. Here, this is the external point, point P. From this external point, point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created here angle APB. Again, this is angle APB that is created by drawing tangent PA and tangent PB towards this circle. Then the angle that will be created between the two tangents, that is to say, this angle APB, it's angle bisector. So the angle bisector of this angle APB must pass through point O, that is the center of this small circle, the center of the circle. Again, the angle bisector of this angle APB must pass through point O, that is the center of this circle. Again, whenever you draw two tangents from a common standpoints towards a circle, then the angle bisector of the angle that was created by drawing the two tangents, the angle bisector must pass from point O, that is the center of the circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing we have, if we focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents towards this small circle, tangent AN and tangent AK. By drawing those two tangents, we created here angle A. Again, this is angle A that is created by drawing the two tangents AN and AK. And according to rule 15, the angle bisector of this angle A must pass from point P, that is the center of this small circle. Again, the angle bisector that was created by drawing tangent AN and tangent AK towards this small circle, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So, you can write down that the angle bisector of angle A passes through point A, and for the angle bisector of angle A passes through point P. The angle bisector of angle A passes through point P. This is the correct page. The angle bisector of angle A passes through point P according to rule 15. Again, the angle bisector of this angle A passes through point P, that is the center of this small circle. Likewise, if you continue to focus on this common standpoint, point A, from this common standpoint, point A, we have here two tangents towards this semicircle, tangent AB and tangent AH. By drawing the two tangents AB and AH, we created the same angle A. Again, by drawing the two tangents AB and AH, we created the same angle A. Now, therefore, we can implement here rule 15. According to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle, angle A, that was created by drawing tangent AB and AH towards this big semicircle. The angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So in conclusion, we can write down that the angle bisector of angle A passes through point Q, that is the center of this semicircle, big semicircle, according to rule 15. In conclusion, we can say that the angle bisector of this angle A must pass through point P and through point Q. It is obvious that the angle bisector of angle A also must pass through point A. So I know that the angle bisector of angle A passes also through point A. In conclusion, we should find out that the angle bisector of this angle A passes through points P. The angle bisector of this angle A passes through point A, P, and Q. But we also know that the angle bisector of any angle is a straight line. And therefore, the 3 points A, P, and Q are located on the angle bisector of A, that is a straight line. Or the 3 points A, P, and Q are located on the same straight line. That is the angle bisector of angle A. Okay, so we can write down here that the angle bisector of angle A, the angle bisector of angle A passes through points A, P, and Q, and because of the fact that the angle bisector of any angle is a straight line itself, therefore all the 3 points are located on the angle bisector of A, so all the 3 points are located on the same straight line. All the 3 points A, P, and Q are located on the same straight line. Okay? And, or in other words, we can write down that all the 3 points A, P, and Q are located on the same straight line, or line segment APQ is one straight line. Again, line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. Again, if line segment APQ is one straight line, it means that AQ is also a straight line. If AQ is a straight line, it means that shape ABQ is a right angle. Again, if AQ is a straight line, it means that shape ABQ is a right angle. If we actually found out that shape ABQ is a right angle. So in the right angle ABQ, this is angle theta, but this angle theta is a common angle that belongs also to the small right angle A and P. Again, angle theta is a common angle that belongs to two triangles, to the small triangle A and P, and also to the big triangle, triangle ABQ. So, in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, this equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this right small triangle A and P. The small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus theta, according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the big right triangle ABQ is similar to this small right triangle A and P. So why the big right triangle ABQ is similar to this small right triangle A and P? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we found out that all the triangles in the right triangle ABQ are correspondingly equal to all the triangles in the right triangle A and P. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, We actually found out that the right big triangle ABQ is similar, this is the sign of similar, to the right small triangle A and P according to angle similarity rule. And from the fact that the right triangle AP is similar to the right triangle ABQ, we'll derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABQ over side AN in the small right triangle AP equals to side BQ, the right big triangle ABQ, over side NP in the small right triangle ANP. I repeat again, we will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB 6, AN is the missing side, so we will leave it as it is. BQ is the radius of this semicircle, that equals to 3. BQ is 3, and NP is the radius of this small circle, that is equal to A. A is the radius that we are looking for in this question. So in conclusion, we should found out that 6 over AN equals to 3 over A. Again, 6 over AN equals to 3 over A. Here we cross multiply this equation, and we actually found out that 6 times A equals to 3AN. Again, 6 times A equals to 3AN. Here we divided this equation by 3, and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we actually found out that this missing side AN equals to 2A units in its length. You know that AB equals to 6, AN equals to 2A, and therefore the missing 9, 7, and B must be equal to AB minus AN. AB is 6, AN is 2A, so in total NB equals to 6 minus 2A. NB equals to 6 minus 2A. In the next step, we did the construction, but before that, so we did the construction from the center of this small circle, that is to say from point P, we draw perpendicular on BQ. Again, from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we can do quadrilateral NP BQ. NP BZ. Inside quadrilateral NP BZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral NPBZ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ. But NPZ, therefore BZ must be also equal to A. Likewise, according to the sum rule, in the sum rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of this side ZQ? From the domain it is very easy to see that ZQ in total equals to DQ. What is the length of side ZQ? ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. BQ is 3, BZ is 8, so in total ZQ equals to 3 minus A. Okay, ZQ equals to 3 minus A. We already found out that PZ equals to 6 minus 2A. What is the length of PQ? We find out the value of PQ by implementing rule 10 in our drawing. Actually, we have an external line between this small circle and this big semicircle. That is to say, they are touching each other externally at point N. And whenever you have an external line between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass through their touching point. So in the drawing we have two circles. Those two circles have an external between them, and this point P. That is to say they are touching each other externally. This point P. The center of this small circle is there at point M. The center of this big circle is there at point O. And the straight line that connects the centers together is of course the straight line MO. According to this rule 10, this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external between this small circle and this big semicircle. That is to say they are touching each other externally in this point L. And according to rule 10, we know that the center of this small circle is at point P. The center of this big semicircle is here at point Q. And the straight line that connects the centers together is of course the straight line PQ. This straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, it means that PQ is also a straight line. But what is the length of PQ? If because of the fact that PLQ is one straight line, it means that PQ will be equal to PL plus LQ. Again, PQ will be equal to PL plus LQ. So PQ equals to PL. PL is the radius A. That is the radius that we are looking for on this question. This is the radius A of this small circle. And LQ is the radius of this big semicircle, that is equals to 3. So total PQ equals to PL, that is A, plus LQ, that is 3. So total PQ equals to A plus 3. So actually found out that the hypotenuse of the big right triangle of the right triangle, again right triangle PZQ, PQ, the hypotenuse PQ is A plus 3. In the next step, I copied this green right triangle in a new page, and we implemented the Pythagoras theorem, this right green triangle PZQ. So actually, this is the right green triangle PZQ that I copied from the original drawing. I repeat again that the hypotenuse PQ equals to 3 plus A, PZ equals to 6 minus 2A, and ZQ equals to 3 minus A. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. So PQ is 3 plus A, therefore PQ square is 3 plus A square, and it must be equal to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square. Plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. So in conclusion, we found out that according to the Pythagoras theorem, 3 plus A square equals to 6 minus 2A square plus 3 minus A square. Here we open the brackets on both sides of this equation and finally found out actually that 3 plus A square equals to 3 square, that is 9, plus A square plus 2 times 3 times A, that is 6A, and it is equals to, on the other side of the equation we have 6 minus 2A, 6 minus 2A square. 6 minus 2A square equals to 6 square, that is 36, plus 2A square, that is 4A square, minus 2 times 6, that is minus 12 times 2A. Minus 12 times 2A is minus 24A. Plus 3 minus A square. 3 minus A square equals to 3 square, that is 9, plus A square, minus 2 times 3 times A, that is minus 6A. Here we have 9 on both sides of the equation, so 9 we get cancelled, and we also have A square on both sides of the equation, so A square also we get cancelled. After we cancel those two expressions, we left only with 6A in this side of the equation. On the other side of the equation we have 36 plus 4A square, and here we have minus 24A minus 6A is minus 38. So in total we found out that 6A equals to 36 plus 4A square minus 38. Here we subtracted 6A from this equation. After we subtracted 6A, in this side of the equation we left with nothing, that is to say 0. In the other side of the equation we have 36 plus 4A square, and minus 38 minus 6A is minus 36A. So in conclusion we found out that 36 plus 4A square minus 36A equals to 0. Here we divided this equation by 4, this quadratic equation by 4, and we actually found out that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and 36 over 4 is 9. In conclusion, we actually found out that a squared minus 9a plus 9 equals to 0. So actually, this is a quadratic equation. A squared minus 9a plus 9 equals to 0 is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a. Therefore, x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And finally the coefficient c equals to 9. The only thing that is left to do is to put the data from our specific quadratic equation inside this general formula for x, and we will find out the value of the values of a, because the variable that we are looking for in our specific quadratic equation is a. Therefore, x equals to a. So we did it, and we found out actually that again x equals to a, so it is a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. C is 9, so minus 4 times 9 is minus 36. So inside the root we have in total 81 minus 36 over 2a. A is 1, so 2a is 2 times 1, that is 2. So here we have two solutions. Actually here we have a equals to 9 plus minus 81 minus 36 is 45. So inside the root we left only with 45. In conclusion, we found out that a equals to 9 plus minus square root of 45 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2, but this expression, that is the radius of the small circle, this expression is greater than 3. But the radius a of this small circle can never be greater than 3 because of the fact that the radius of this big semicircle equals to 3. And the radius of this small circle must be definitely less than 3 units, because it is less than the radius of this big semicircle, that is 3. So the possibility that the radius a of the small circle is greater than 3 is the incorrect possibility. We cancel the solution, and we left only with the second solution that is possible for a. The second solution that is possible for a is the radius of this small circle. So the radius a equals to 9 minus square root of 45 over 2. 45 is 9 times 5, so we substitute 45 by 9 times 5, and we actually found out that a equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so in total the value of this expression is 3 times square root of 5. So inside the root we have only 5 divided by 2. In conclusion, we actually found out that the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, the radius a of this small circle equals to 1.146 units. Okay, thank you very much.